So this lecture deals with elimination of epsilon transition from a given finite automata. So you are given an epsilon NFA. Aim is to eliminate epsilon transition from this finite automata. So first you have to determine or find the equivalent states in our finite automata without epsilon transition. So for that you can compute epsilon closure of each states in our finite automata, that is epsilon closure of Q0. So epsilon closure of Q0 is the set of states that are reachable from Q0 through epsilon transition, and from Q0 without consuming anything or through epsilon transition it can reach Q0 only. Now what about epsilon closure of Q1? So epsilon closure of Q1 is the set of states that are reachable from Q1 through epsilon transitions including Q1. So anyway Q1 will be a member. Through epsilon transition it can go to Q2 also. So Q1, Q2 will be epsilon closure of Q1. Now next compute epsilon closure of Q2. So epsilon closure of Q2 is actually set of states that are reachable from Q2 through epsilon transitions including Q2. So from Q2, anyway Q2 will be a member. From Q2 through epsilon transition it cannot move anywhere. So these are the epsilon closures of states Q0, Q1 and Q2. And remember that these are the states in our equivalent finite automata without epsilon transition. So let us construct the transition table parallelly. So you are having set of states in the first column. So this is the first state. So this is actually a notation. So the equivalent finite automata without epsilon transition consists of states which will be represented as subset of states in our epsilon NFA. So we are having Q0. Then next state will be Q1, Q2, Q1, Q2, and next state will be Q2. So once after identifying the states, you have to differentiate the start state and you have to differentiate the final states. So epsilon closure of start state in our epsilon NFA will act as the start state in our NFA without epsilon transition. So this is actually epsilon closure of the start state in our epsilon NFA. So this will act as the start state in our NFA without finite automata without epsilon transition. Now you need to identify those sets containing the final state in our epsilon NFA. If you consider this epsilon NFA, Q2 is the final state. So you can mark those states containing Q2 as a member as final state. So if you analyze this set, Q2 is a member, so this will be a final state. If you analyze this set, Q2 is a member, which is a final state in our epsilon NFA. So you can mark this as final state. So in the equivalent finite automata without epsilon transition we will be having two final states. Now let us apply all transitions, that is A, B and C trans. If you analyze this finite automata, you are having three input symbols A, B and C. So you are expected to apply those inputs to the states in our finite automata without epsilon transition. You are having A, B, C inputs. Now how to apply input A to each and every state? So let delta dash be the transition in our finite automata without epsilon transition. So delta dash is the transition function. So you are going to apply delta dash to the state Q0, you are applying input A. So you can expand this transition function like this. This will be equal to epsilon closure of delta. See, delta is actually the transition function in our epsilon NFA. Delta delta Q0 A. So you are applying, first you have to apply transition function delta to Q0 A, and to the result you have to take the, from the result you have to take the epsilon closure, and that will be the target state. So this will be equal to epsilon closure of, so what is delta Q0 A? Delta Q0 A is, delta Q0 A is set Q0 Q1. From Q0, by consuming A, it can go to Q0 and Q1. So how will you expand this? This will be equal to epsilon closure of Q0 union epsilon closure of Q1. So this will be equal to, what is epsilon closure of Q0? Epsilon closure of Q0 is, epsilon closure of Q0 is set Q0 union epsilon closure of, what about epsilon closure of Q1? Epsilon closure of Q1 is Q1 Q2. So this will be equal to set Q0 Q1 Q2. So you are getting the set Q0 Q1 Q2. So epsilon closure of Q0, which is equal to Q1, sorry Q0, epsilon closure of Q1, epsilon closure of Q1 is Q1 Q2, epsilon closure of Q2, which will be equal to Q2 itself. So this will be the target set. Now let us apply B transition to first state. So if you apply B transition to the starting state, you can expand this as epsilon closure of delta Q0 B. So this will be equal to epsilon closure of, what about delta Q0 B? To state Q0, if we apply input B, there does not exist any B transition, so that will be null set. So epsilon closure of null set is null set itself. So this will be empty. Now you have to apply C transition. So epsilon closure of Q0 C, that will be equal to epsilon closure of, sorry, delta dash Q0 C, that is epsilon closure of delta Q0 C. To state Q0, there does not exist any C transition, so this will be null set. So epsilon closure of null set, which is null set. So delta dash Q0 C is null set. Now we can consider the next state. Next state is set Q1 Q2. So to this state you have to apply input A, that is delta dash Q1 Q2 A. So how will you expand this? This will be equal to epsilon closure of delta. So you are having in state Q1 and Q2 in this set. To this state apply input A, Q1 A union. Now to this state apply input A, that is delta Q2 A. That is, as I said, delta is the transition function in our epsilon NFA. So apply A transition to Q1, apply A transition to Q2, take the union and take the epsilon closure of the resultant set. So this will be equal to epsilon closure of, what is delta Q1A? Delta Q1A is null set union. What about delta Q2A? Q2A is also null set. So this will be equal to epsilon closure of null set, which is equal to null set. So this will be empty. Now apply B transition to this state. So that will be delta dash q1 q2b will be equal to epsilon closure of delta q1b union q2b. So what is delta q1b? Delta q1b is set q1 union. What about delta q2b? Q2b is null set. So this in turns epsilon closure of q1. So what about epsilon closure of q1? That is q1 q2. Set q1 q2. So here target state will be q1 q2. Similarly, apply C transition to this state. So what happens if you apply C transition? So delta dash q1 q2 c will be equal to epsilon closure of delta q1 c union delta q2 c. So what about q1 c? To state q1, if we apply input c, there does not exist any C transition, so that will be null set union. What about delta q2c? To state q2, if we apply input c, it will remain in the same state q2. So this will be equal to epsilon closure of null set union set q2, that is q2 itself. So epsilon closure of q2. So what about epsilon closure of q2? That is equal to set q2. So here it will be set q2. Now you have to consider the third state in our finite automata without epsilon transition. Apply transition function, that is delta dash q2. First you have to apply a input. So this will be equal to epsilon closure of delta q2a. So this will be equal to epsilon closure of, what about delta q2a? Q2, there does not exist any A transition, so that will be null set. So this will be equal to null set. Epsilon closure of null set is null set. Similarly, apply input b. Delta dash q2b. Set q2b. So this will be equal to epsilon closure of delta q2b. So what about q2b? There does not exist any B transition, so this will be null set. Epsilon closure of null set will be null set itself. Next one is delta dash, you have to apply C transition to this state. So delta dash set q2c. So this will be equal to epsilon closure of delta q2c. To state q2, if you apply C transition, it will remain in the same state q2. So epsilon closure of q2, epsilon closure of q2 is q2 itself. Okay. So in this way you can build the transition table of equivalent finite automata without epsilon transition. Now how will you represent this transition diagram using, transition table using transition diagram? So you are having states with label set q0, you are having set q1, q2 as another state, and here you have marked this as final state. You are having another state set q2, that's also a final state, and q0 is the start state. Now add transitions one by one. So from this state label set q0, if we apply input a, it actually goes to this set q0, q1, q2, set q0, q1, q2, and you are not having a state with label like this. But if we analyze this particular set, that is set q0, q1, q2, this is actually union of these two states. So you can treat this as set q0 union set q1 q2, in the sense from q0, if we apply input a, it will remain in the same state q0 or it will go to state q1 q2. That will be the transition. So from q0, if input is a, it will remain in the same state or it will go to state labeled set q1 q2. Now you don't need to bother about this null set. Null set, there does not exist B transition from this state, and there does not exist C transition from this state. That is the meaning. Now you can consider state Q1, Q2. To state Q1, Q2, if we apply input A, there is not exist in transition, so you don't need to bother about it. To state Q1, Q2, if you apply input B, it will go to state Q1, Q2. That is, B transition will remain in the same state. Now, to state Q1, Q2, if we apply input C, it will go to state Q2. Now, to state Q2, if we apply input A, there is not extend such a transition. To Q2, if you apply input B, no such transition. To Q2, if you apply input C, it will remain in the same state. So this is the equivalent finite automata without epsilon transition, and if we analyze this one, this is not a DFA, this is actually a non-deterministic model. You are having multiple A transition from state Q0, that actually leads to non-determinism. But this finite automata does not contain any epsilon transition, and you can verify whether this model accepts everything accepted by this model. So let us consider the string A, B, C. A, B, epsilon transition followed by C. See, this accepts A, B, C. So this accepts the string A, B, C, which is accepted by epsilon NFA. So from this it is clear that if you are given any epsilon NFA, you can eliminate that epsilon transition so that you will end up with a finite automata. It could be NFA without epsilon transition, or sometimes it will you will end up with a deterministic model. In all cases, you don't. It's not necessary to end up with a deterministic model, but you can simply eliminate epsilon transition from the given finite automata. So, from the design point of view, if you want to solve a problem using a deterministic finite automata, rather than designing a deterministic model, you can easily design epsilon NFA, eliminate epsilon transition, you will end up with NFA, and convert NFA to DFA, you will be getting a deterministic model. And it is clear that epsilon NFA and NFA are equivalent in terms of power, since there exists a systematic procedure to eliminate epsilon transition from the given finite automata.